Good morning. Today I'll be talking about radio frequency absorber design and analysis, and that will be used for RF energy harvesting applications. The topic has been inspired from real life example such as our retina. We are able to get image through retina, and similarly we can also get imaging through RF absorber, and if we apply these RF absorbers for detection, then the imaging becomes possible. As we are aware that our retina has more than 100 million rods and 5 million cones. These rod cells are composing the biological pigment, as well as these cone cells are color specific. The pigmentation is same, only the difference between rod and cone is the visible frequency wavelength. Both wavelength lies in the spectrum of 300 nanometer to 700 nanometer. We are already aware that the photons are being incident on the periphery as well as center part of our retina. In periphery we have gray cells rods, and these gray cell rods has 10 layers of the pigment. The moment the photon is incident on the rod cell, it passes through the 10 layers and gets converted into X-ray potential. These X-ray potentials are also termed as neurons, and these neurons get traveled through optical nerve to form a image element. That image element is nothing but a detected photon. And in similar way, the cone cells are three variant in the center of the retina, and these three variant differ in wavelength. The moment the photons hit to specific cone cells, they are also passed through these 10 layers of pigment, and then gets converted into X-ray potential. This X-ray potential is nothing but a neuron. So this way we are able to get a detected a pixel value or neurons of three different wavelengths, and that becomes a matrix in the brain which passes through the optical nerve. So this way we are able to get the object image in our retina with the help of our brain. So the topic has been inspired from the human retina, and now we will discuss the basic principle and working of RF absorber for energy harvesting applications. As you see in the slide, the title is being mentioned here. In this, we will describe how the RF absorber operates, and then with the help of rectifier circuit, how can we convert this absorbed or received voltage into DC voltage, and then the low voltage DC will be available to operate IoT device. So the excellent application of this RF absorber is for IoT devices where there is no cell required, only the operating voltage will be the radio frequency. So these small IoTs which are being used in smart city, smart home, healthcare applications can be converted into self-sustainable IoTs by making use of RF absorbers or receive-only antenna. These are also known as rectina. We will describe how these devices help us to collect or to accumulate the energy in terms of DC voltage from the ambient environment, or it can also be a developed system using the intended RF energy to be radiated in the environment, and then at certain distance we can place these self-sustainable IoTs so that they operate 24/7 with this radio frequency harvested voltages. So in detail we'll discuss in this today's topic. I'll be highlighting the RF absorber design, 2.4 gigahertz and 1.6 gigahertz design I'll be exploring. Reason being, the 2.4 gigahertz is used for in-house Wi-Fi devices, and 1.6 gigahertz is generally used for GPS reception. So both frequencies are available. These frequencies fall in ISM band. Now, the second part will be how can we design using software. That also we can discuss. Then what is the basic technology of the RF absorber. Then we will describe various characteristics of RF absorber. In detail, we will talk about the mathematical part of the design, and in last we will see that these RF absorber can be made in applications for imaging, sensing and energy harvesting. It means with the help of these RF absorber, if these are being placed at Wi-Fi or GPS frequency, they will be acting as receive antenna in association with the rectifier, and the DC voltage will be available. Either we can say the low voltage DC will be available, which will make our smart city or smart home or healthcare sensors as self-sustainable sensors, and there won't be any external supply or battery will be required, because the battery gets frequency drained out, and we need to change those batteries now and then. With the help of this radio frequency harvesting, these small devices or IoT devices can operate around the clock, and there is no need to change the batteries. It means the energy life is very large in this way. So how the RF harvester works. In RFG harvester, we'll see there are few important parameters such as the absorbance, the reflection coefficient, that is S11, and transmission coefficient S21, the DNG parameters. DNG is nothing but double negative parameter, such as negative permittivity and negative permeability. These materials are not available in nature, but these are artificially altered or artificially created materials. By creating the characteristics of permittivity and permeability in negative, or their coefficient is being converted negative, how we make use of split ring resonator, that is known as SRR. Another terminology being used for SRR is ERR, electrical ring resonator. Sometimes these are also known as FSS, frequency selective surfaces. Sometimes we recall them that these are HIS, high impedance surfaces. So various various shapes and various metamaterial absorbers are available. We can choose a particular shape or particular material. We'll discuss how these materials will differ in shape, size, and the material characteristics, and then based on that, what we will be able to get from these metamaterial absorbers, that the incident electromagnetic wave phase angle will get altered. So generally the EM waves follow Snell's law, but by making use of these metamaterial characteristics, they will no more follow Snell's law. In place of that, they will behave differently as far as phase is concerned, and by altering that phase, we will have absorption coefficient larger, and we will see that these reflection coefficient and transmission coefficients are being nullified. So at optimum we can get unity absorbance. How, that we will discuss in coming slides. See, basically, if we see this particular slide, here we have shown architecture of the absorber. If you see figure 1, there is a FSS on the top, there is a absorbing material or substrate in the center, and there is a PEC or metallic part at the bottom. So when the incident wave, electromagnetic wave, strikes to FSS or metamaterial structure, it is being received. So a electrical charge will get accumulated on the structure, that is FSS, which is also known as SRR or ERR, will be frequency specific, means these are being designed for a particular frequency. Maybe in our example, either these are designed at 2.4 gigahertz or 1.6 in case of GPS frequency. So these are also termed as resonant surface. So the incident waves strikes to the FSS because the metamaterial characteristics are available in this FSS. So the incident phase angle, in place of getting reflections, it being traveled into the dielectric material, and then at the back there is a PC or copper, they get reflected and again travel to the substrate. Then there is a FSS, again the FSS will force the EM wave to travel into the substrate, and this process continues because the EM wave which is being received by FSS travel into dielectric material, which is also known as absorbing material, will offer certain loss, that is also known as dielectric loss, as well as on top of the FSS there will be, because these FSS are of metallic, they will offer some sort of resistance, and this way the charge gets converted into currents, and these currents when travel through the conducting surface and the dielectric surface will offer two different losses. One is dielectric loss and another is conduction loss. So here in FSS or in absorber we will see that the surface current form a loop current, and because of this loop current there will be a attenuation or absorption being offered by the dielectric material. So we feel that the loss which is being offered to the surface current or loop current will be termed as absorption. And this is the basic principle of the RF absorber. If we see the next slide, here we are able to represent a equivalent circuit of RF absorber, where we see that PEC backplate is being represented by the ground plane. In center, ZM represents the substrate impedance. And in the incidence FSS, ZFSS represent the impedance of FSS. In figure C, we see that this is a fluctuant port which represents the TLM transmission line model, and this transmission line model represents how the absorber is being constituted. This model is being developed using CST software. Now if you see in this slide, this is absorber which is being represented by ADS software. So as shown in figure B is being represented by the absorber RLC circuit, and if we see the simulation we can get S11 as the graph being represented here. So S11 we can get either from CST or from ADS Agilent software, and we can compare the result which will give us a tuned resonant frequency characteristics. As we see here in this particular figure, the 1.6 frequency we are getting the SS1 lesser than minus 10 dB. It means this is resonant at this particular frequency. Now coming back, the characteristics or the process of RF absorber. Now we see A is equal to 1 minus S11 mod square minus S21 mod square. The refractive index is negative because these are artificially created created, so negative permeability and negative permittivity is being obtained by choosing the metamaterial SRR for a particular frequency. If we see the metamaterial figure in coming up slides, that the microstrip line will represent inductance and the gap created in microstrip line will represent capacitance. So SRR or ERR is nothing but a combination of inductance and capacitance. Now, if these inductance and capacitance are being connected in series, we already know that will be resonant particle frequency, and the frequency formulation will be F is equal to 1 upon 2 pi root under LC. So L and C part will be responsible for a particular frequency to operate. So the design frequency of SRR will be depending on at what frequency we are designing. So length of inductance and the gap of capacitance will constitute a frequency parameter. If we see the second point, the phase of signal advances as incident wave captured by FSS. Coupling due to resonance into dielectric causes circulating loop currents to form surface current from the radiations from the free space. Point number 3, an anti-parallel surface current dissipation takes place between FSS and ground plane. Point number 4, the effect of dielectric loss, as already told to you, and conduction loss is being forming the value of the absorbance. Impedance matching is crucial part because the total input impedance of the absorber must be equal to free space impedance, that is 377 ohm. Now, attenuation of EM wave takes place due to lossy substrate material and due to electric and magnetic response of the metamaterial surface, that these also can be termed as TM or T responses. Now, based on that, these are the following characteristics. T mode or TM mode excitation using Fleckit port is being done in RF absorber. The reflection coefficient and transmission coefficient must be as minimum as possible. These can be achieved by quietly matching the FSS structure for a particular received signal and choosing a particular type of absorbing material, that is also known as substrate. SRR, substrate, both must be backed with a metallic surface, that is PC or Z is equal to 0. The absorption investigated using E field, H field and surface current density on both T mode or TM modes. Strong absorption will take place when impedance match is perfect with the free space impedance. The very important and crucial parameter for RF absorber is that it must be insensitive to the angle as well as polarization of the incident wave. We generally feel that if the mechanism of circular polarization and wide angle response is being created into absorber, it means from any part the incident EM wave will be absorbed by the absorber. Reason being, the absorption coefficient in particular direction is maximum, but if it is less in at any of the angle, it means then absorption or absorber will not be the suitable for certain applications. Now, if we see this particular slide, this is a RLC equivalent circuit which represents the series and parallel combination of RLC lumped constants. The net effect of these RLC circuits, which are being obtained using EDS software and simulated with CST parameters, because CST we designed a RF absorber and in ADS we designed an equivalent circuit corresponding to CST software, and then we obtained simulation using reflection coefficient and then compare the features. So in this particular diagram we represent that a peak in reflection coefficient or S11 or return loss is being seen at 1.6 gigahertz. Now, same thing can be verified using H field, E field and surface current simulations using CST software. Now if you see here, E field animation is representing the response of TM mode, as well as H field animation is representing T mode. These both simulations are being carried out using CST software. Now same thing can be seen with the ground plane, that the surface current J animation is representing. Now we have already seen that E field and H field at a particular frequency. Now we will see that both frequencies simulation in one particular diagram. Here we see that E field animation into substrate, where the dielectric loss is taking place. Similarly, H field animation being opted into the substrate. It means that the RF absorbers are resonant at particular frequency, and they will be responsible for absorption or absorption coefficient, or these will be specific to the received energy. We can call these absorber as receive only antenna. Now in case of energy harvesting, the received energy or received power PR will be converted using rectifier circuit into DC voltage, and then DC voltage will be connected to the load can be small IoT. Now here main problem is that the received signal of receive only antenna is very less, and then the very less power will be converted into corresponding DC voltage. It means we need to have the efficient rectification. Now for efficient rectification, either we can use Schottky diode or we can use CMOS based rectifiers. So how the complete process takes place will be discussed in the next class, but here only we want to convey that these absorber designed for a particular frequency can be made available to convert this received power from the ambient environment into corresponding low DC voltage, and these low DC voltage can be used for various applications like sensors, IoT device, healthcare device. That's all for this particular lecture. Thank you very much.